Roden Schwartz is a leading manufacturer of value instruments designed to help you maximize your bench's performance for everyday applications. They just announced an industry first, complete solutions with all the upgrades up front for one price. Now through December 31st, 2019, save up to $10,000 on Roden Schwartz solution packages that come with fully loaded test and measurement instruments right from the start. When you invest in Roden Schwartz products, you get the highest quality engineering, plus all the bandwidth, channels, inputs, memory interfaces, and signal generation you'll ever need. Learn more about Roden Schwartz value instruments and this limited time promotion at askanengineer.us. That's askanengineer.us. This is the Amp Hour Podcast. Released October 20th, 2019. Episode 463. An interview with Trammell Hudson. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Trammell Hudson, a hardware and firmware security researcher, and I like to take things apart.
Hey, Trammell, welcome to the show. I've admired your work from afar for a long time.
Yeah, thanks for having me. It's really a fun chance to get to chat about some of the projects, and I think we have a lot of interests in common.
Yeah, I think so, and I think that we have a lot to talk about too. Your site is a repository of hacks and a variety of interests that we're going to go through, and it's really, really fun to follow your site. So it's trmm.net for people who want to follow along at home. We'll be going through some of the projects there. But why do you do all this stuff? I mean, you do a lot of different things and you document it really well, and that's not necessarily the most common thing. How did you get into hacking and documenting all these things that you do?
Well, the main reason I like to document everything is because my attention span is really short. So Charles Strauss jokes that people like me fail our saving throws versus the next shiny thing too easily. And so usually after I have a project sort of to the proof of concept stage, I like to photograph it. I like to write up about it. I like to push everything to GitHub or somewhere, and then move on to the next thing. And over the past 10 or 15 years, I've been doing a lot of projects like that. So most of the time they get to the point where they work for me, and I hope that they are going to work and be helpful for other people. And it's really a delight when I get email from people who have picked up my other projects and used them in their own, or they've extended them. I joke that my favorite day is starting a new project, and my second favorite day is handing the commit keys over to somebody who wants to maintain it and turn it into something even better.
Yeah, it's like owning a boat. The best days are when you get it, when you sell it. Apparently, I've never had a boat.
Yes, I think it's a similar sort of thing that I really love the finding out how things work. I really like to take things apart and dig through the firmware and understand what makes a lot of these devices function. One of my real passions has been in making it possible for people to run their own firmware or extensions on firmware on devices that they've purchased. And this is a lot of fun for me because it lets me focus on the interesting part of how do we get inside some of these systems. And then it lets people turn the devices they own into things that are more functional for what they want to do with them. So a lot of the projects have that sort of focus.
Yeah, and I'd love to hear about so I definitely want to talk about the individual projects themselves, but up front, I'd love to hear about, when I think about reverse engineering and I think about, the kind of stuff that you work on, you talk about troubleshooting a lot too. You gave a talk about I think it was the joy of taking things apart. That's kind of a great overview of your thinking, at least as far as I could tell. But the thing I always think about is like the amount of stick-to-itness or mental fortitude, or just like, staying in that discomfort. First off, how do you deal with it? And second off, how did you get to the point where you like staying in it? I always kind of get frustrated myself and I kind of jump out of it a little too soon. So like, how do you think through a problem and stick to it so that you're getting that first piece of firmware on there?
There's a wonderful quote by Matthew Garrett about that he doesn't think he's very good with computers. He's just really bad at knowing when to give up. And I think that uh, I share that sort of attitude towards it. Um, the I think one of the reasons I tend to stick to it long enough to get things working is I've had enough success in the past that I feel that once I find the sort of the first way to get some code execution or to get a better picture of what's going on inside a system, I have a good feeling that I'll be able to do more with it. And we found that a lot in like when we do classes at NYC Resistor, the hackerspace that I used to belong to, that if people have enough early success, that they're able to stick with things further and power through the adversity of sort of the next levels. And I think after doing enough of these projects, I feel that I can have a good feeling that of seeing the light at the end of the tunnel and seeing that end goal of going beyond the hello world. Um, but a lot of
Mm-hmm.
times, things don't pan out, and I try to document a lot of my failures as well. Perhaps they'll be helpful for someone else. Perhaps they'll be a warning for someone else.
I think the documentation itself is actually a troubleshooting method, and like it seems like that's kind of how you think through problems, or you're able to capture what you're working on, and that kind of helps you to probably come back to it as well.
And having good notes definitely helps out with figuring out what have I tried and where are some ideas to try some other paths. So it serves both for me to keep track of what I'm doing, and then, like I said, hopefully it helps other people as well.
So, what were some of the early successes that you talked about that kind of gave you the confidence to keep going?
So the one that I had the most success with was the Magic Lantern firmware for the Canon cameras, and that came out of seeing the CHDK project, which was building GPL firmware for some of these cameras, or excuse me, for the point and shoot cameras. So I had a good feeling that it was possible to do a similar thing for the SLR, the higher end SLR cameras. And the
Mm-hmm.
motivation that I had was that the initial firmware from Canon had a lot of limitations, and at the time I was trying to make some short films and involved in that community, and there was a lot of complaints about the fact that it didn't have on-screen audio meters or manually controllable audio levels, and I knew that was just a simple matter of programming. So based on what the folks on the CHDK site had done, I was able to understand a little bit about the Canon's firmware update files and able to apply what they had documented to stand on their shoulders and extend all of that for the SLRs.
So, how much of it does so you said CHTK? Is that right?
Uh,
Is that the
CHDK. It's the Canon Hackers Development Kit.
DK? Okay, sorry. So, how much of that? So, like you're approaching a problem like this, you're taking an off the shelf consumer level well, maybe prosumer level, I guess that's a nice camera. How much do you have to know about the actual hardware? I mean, are you taking a camera apart? Do you need to know the processor, or is it more about dumping firmware files and just kind of operating within the scope of what firmware you see?
It's mostly dealing with the firmware side of it. That the since a lot of these devices have firmware updates that the vendors ship, that gives us a something that we can look at to try to understand what's going on inside. Um, but it's not always that case. That some of the other firmware dumps have involved, say, getting a little bit of code execution and then toggling the rest of the firmware out via a LED or a GPIO line. So it's not always as easy as being able to download a firmware from the vendor website. Uh, but typically, it very quickly moves from that sort of hardware work to using a disassembler like Hopper or IDA or the new one from the NSA, Ghidra, to try to make sense of the firmware and figure out how it's constructed, what the sort of various what the programming model inside was, so that we can then build extensions on top of it.
And you had mentioned you toggle the entire firmware dump out of the LED. Is that right?
So one of the initial versions of CHDK was yes toggled out via an LED.
That's pretty crazy.
Yeah, I mean LEDs have reasonable amount of bandwidth, so put a photo transistor on there, and you can get a ROM dump.
That's I figured you were like probing onto it, but you're saying you don't even have to. So you're not opening the camera at all in some of these cases.
Most of the time, you don't have to open the camera at all. That's right.
Yeah, I mean, because I mean, I've seen at least images inside cameras, and they're all flex PCBs and tiny circuits, and yeah, and not to mention, cameras aren't cheap, so there's that
Right.
too. Yeah,
One of
yeah.
the consumer devices I'm playing with right now are the IKEA TradFry smart bulbs and LED dimmers, and in that case, in order to reprogram them, I am opening them up and hooking up to the debug port.
Hmm.
And again, we're benefiting from the fact that most of these devices are ARM based, and there are lots of really good tools for working with ARM CPUs and ARM firmwares.
Right.
So it's pretty easy to disassemble it, figure out what needs to be patched, and then using either SWD or JTAG or something to be able to flash a new modified version back onto the embedded device.
Yeah, and what about like locking and stuff like that, like security bits and firmware locking, and how do you deal with that usually, if it exists?
So that sort of segues into my other area of research, which is boot time security on devices. Uh, so I gave a talk recently at Hack in the Box here in Amsterdam about a time of check, time of use vulnerability that I found in Intel Boot Guard, which is attempting to do a signature verification on the on the flash that it's using to boot from the firmware, and due to an issue in the way that the cache's RAM, the cache invalidation happened. It ended up fetching a few instructions a second time from the flash after it had already checked the signature on them, and that
Huh.
was enough to be able to replace those instructions with my own that would jump somewhere else in ROM, and then gave us code execution.
So is that because the first time it's checking that the stuff is valid, and then it says, oh, it's good. Whatever comes after this is cool, and then you put something different in there.
It's that it checks the signature on it, and then it tries to run the code that it has validated the signature on. And so it's a time of check, time of use error, where if you can change what's in the ROM between when it has checked that signature and then when it goes to execute it, you can have it execute your code instead.
How do you start to look at that something like that might even exist? Are you just kind of following along the boot pattern and trying to figure out where there might be a time to insert reverse engineered code?
So in that case, I do a lot of work on a project called Linux Boot, which is a replacing x86 firmware with open source software. And because I ended up having to reflash these chips all the time, I built a piece of open hardware called the Spy that will log all of the flash memory accesses and then be able to provide them from an emulated DRAM rather than from flash memory. And as part of building that, I noticed that there were some addresses that were being read twice from the flash chip. And again, going in with the disassembler, I was able to track down that that was a code fetch, not a data fetch, and that it had happened after that signature validation. So this is the case where we built a tool for to speed up firmware development that then revealed a security vulnerability, and then spent uh, almost 10 months working with Intel for them to come up with a patch
Oh
for it.
wow, yeah, that's pretty intense. What does the Spy look like? What is it like? What is it developed with?
So it's built on the ECP5
Oh, cool.
FPGA. There's a Croatian hackerspace, Radiona, that has made a really nice development board with the Lattice ECP5, 32 megs of DRAM, and a bunch of other fun things. It has HDMI and micro SD and whatnot. Um, so I gave a talk at CCC Camp about the Spy and the difficulties in emulating the flash chips. So there's a really hard real-time task where you have to be able to um, serve up a response from the memory in basically one clock cycle, which could be just tens of nanoseconds. And most DRAM has hundreds of nanoseconds of latency. So developing this in an FPGA allowed us to build our own memory controller that could uh, do some interesting cheats to meet that timing requirement.
Yeah.
And so this is fun because it's open source software running on open hardware using the open source FPGA toolchain from Yosis and Project Trellis and XPNR. And again, it's really amazing how much uh, you know we're able to use these open source projects to stand on their shoulders and uh, make things that would be very, very complex if we had to do it all from scratch.
So let's hear about that memory controller then. So like internally, so you're saying that you have to basically have like the response kind of built into the logic fabric. Is that how it's fast enough, or like how do you get that? What are those cheats that you mentioned?
So the big cheat is that DRAM, when you do a read from DRAM, it's a multi-stage operation that we think of in a normal programming language. You read from an array. That's one sort of atomic step. The address goes off to the memory controller. Data comes back. But under the covers, DRAM has a row activation stage where it has to copy the bits from the capacitors where they're stored in the actual dynamic RAM into registers, and then that row activation takes multiple DRAM clocks, and then when you do a read of a column from that row, that again takes a couple clocks to happen. Since we're receiving the address bit by bit on the SPI interface, we can actually start the row activation once we have 15 bits worth of the address,
Oh, nice.
and then we can do the column read once we have an uh, additional 8 bits of the address, and then we can do the final byte select when we get that last bit of the address, and that way we can have the data available for the SPI bus output on the next SPI clock cycle. So it's being able to interface with the memory on that sort of fundamental level rather than on the very abstract level.
Yeah. That is really cool. Okay, and that actually helped clear up too. I was wondering when you were saying like a single clock cycle. So you were saying a SPI read cycle. That's what you really mean. You have to do it by one of those.
That's right. That
Okay.
because you get a 24-bit address,
Uh-huh.
clocked one bit per SPI clock,
Yep.
and so you need to have a result ready, basically from the rising edge of that last bit of the address. You need to have the data present on the output, pretty much on the falling edge of that clock. So you really only have half a SPI bus clock cycle.
Oh, I see. Yeah. So that is still. I was thinking that like the SPI, because like, what is the SPI being clocked at? Like 10, 20, 30 megahertz? I don't know. More than
Yeah,
that?
20 to 80.
Okay. Yeah. I was thinking that it was
Yeah,
like because you get multiples of that, but you're saying that because you have to, you're basically like live decoding that stuff. Then it's from that last one. That's when it like finalizes it, and you're saying it has to pull it all the way back.
that's right. That's right.
Yeah.
So if you had to wait till you had the full address to do the read, uh, the DRAM would delay you hundreds of nanoseconds,
Yeah.
and you really only have about 10.
Got it. Okay.
So
Man, that's a really interesting problem. And then so how does the is this because it is specifically in DRAM versus like uh the normal case, I guess, is like a x86 is going out and reading a SPI flash. Is it like hard coded in the SPI flash normally, or what is the normal case that you're trying to replicate? I guess.
in the normal case, yeah, it's in a. I actually don't know what the internals of the flash memory looks like, but it's able to deliver uh, the data, at this sort of speed. Um, Probably it. My guess is it doesn't have to do this sort of row column activation. That
Hmm.
it's able to actually. I really don't know what they look like inside.
Sure,
Um,
sure, that's fine. Yeah,
m-
that's
my expertise, you know, uh, I haven't pulled apart those chips, and in
yeah.
fact,
So you're just saying
the
though that it is effectively immediately available, and that's what you're trying to replicate.
I think so. If you
Yeah.
had like static RAM, for instance, you'd be able to
Hmm.
do these sorts of reads, these random reads,
Yeah.
without any problem.
Right.
Um,
Yeah, because static
and
RAM
so,
is just actual like flip flops, right? That's what's internal on those.
pretty much, yeah.
Yeah.
Um, but to buy 8 or 16 megabytes of static RAM is pretty expensive.
Yeah, that's right. Yeah, yeah. And so then why do you need that much RAM in the first place? Is it just to do all the computation you're hoping to do, or to have like multiple versions, or why is it a larger RAM set?
Well, the SPI flashes that we're emulating are 16 or 32 megabytes. That
Okay.
we've come a long way from the original 64 kilobyte BIOS chips. That they're now,
Yeah. Right.
they have an entire operating system inside of there.
Well, that's a good segue. So you also do retro computing. Moving along to the next interest of yours. So you've done a lot of retro computing stuff as well. What's your interest there, and like what has been your some of the projects you've worked on?
I'm not really sure why I got into it. I've been for some of them they're not really retro for me because I used them when I was growing up or when I was much younger.
Right.
Um,
Right. Yeah, but contemporary computing just doesn't sound that cool, you know?
and it's uh, one thing that I find really fun about them is how approachable they are. That a modern computer has so many moving parts, and the operating systems are so incredibly complex that an ordinary user can't be expected to understand what all is going on. But with a lot of these old computers, they were built assuming that the computer owners would be knowledgeable about the insides. That many of them shipped with schematics, and people were expected to solder together expansion boards and things. In many ways, the what I really like about the sort of Arduino movement is that it's brought back that kind of playfulness and the expectation that everything has schematics and data sheets. So yeah, with the retro computers, they're mostly understandable, and a lot of things are also then very much fixable because they're built with through hole components or large scale surface mount. The clock speeds aren't that high. They're typically 5 volts or 3 volts, so it's not it doesn't require any uh, high speed differential signaling type things. So
Right.
if something's broken in your antique retro machine, you can probably fix it, or you can build a small microcontroller or FPGA part that replicates the pieces that are no longer functional. Um, and there's a lot of fun uh, areas where people have done exactly that. So disk drives, for instance, have pretty much all failed, but you can buy kits that will give you a emulated SCSI disk so that you can still boot your machine off a solid state drive or compact flash card. Um, the it's possible to build adapters. Say, take a USB keyboard and adapt it to some of the older formats, so that you can still talk to these machines. And when as you start to go even further back, the things like the PDP-11 that we restored just has a regular serial port, so you can hook it up to whatever machine. Um, it's very easy to connect it to a modern computer.
And there's just something fun about, putting a PDP-11 onto a network or doing similar things with that. I mean, they have like their own aesthetic and everything too, and sometimes you find fun things inside. I saw the Easter egg you found in the Mac SE. What, how
Yeah,
did you find that?
so that one was a lot of fun. Where literally found a Mac SE on the side of the road in Brooklyn, and with a failed hard disk and a non-working floppy disk. So we were discussing what to do with it, and one of the hobbies that some of us at NYC Resistor had was dumping the ROMs and digging through them, looking for fun, either fonts or bitmaps or Easter eggs. And Adam Mayer at Resistor noticed that, hey, there was something that looks kind of like faces if you plot these bits out, and that led us down the rabbit hole of figuring out the old Mac pict format and putting together little Python programs to decode them. And the Easter egg itself was pretty well known, that you could get to it through the MacBug or MaxBug debug hardware. So this was just a really fun exercise in understanding an ancient file format and looking for interesting things. And there's also a really fun thing that came out of that are the Mac ROM scarfs from Knityak. Fabienne is doing this cool computational knitwear, and she saw the sort of the black and white ROM dump images that we were making, and converted it into into a physical item, so you can actually wear the bits when it gets called out.
Yeah, Fabienne has been a past guest of the show as well, so people can go and listen to that Knityak episode that is back in 2015. That was episode 257. So we'll link that in the show notes too. But yeah, that's it's kind of weird to think about like wearing code, but it's a fun idea.
And the other fun thing about a lot of those machines is they didn't have a lot of storage space, but they also didn't want to build complicated code. So bitmaps are frequently stored just as literal 1 bit per pixel or 8 bits per pixel. So if you plot them out, you can see the fonts or the images. So yeah, some of the scarves have the Happy Mac on it because it's literally in the ROM, just as a 32 by 32 image.
That's great. That's great because you're saying it's because it's part of the entire ROM image that might be plotted on there.
Right. Exactly. Yeah.
Yeah, and it's interesting too to kind of I feel like the theme I'm seeing with you as well is that you're taking this knowledge, you kind of like not just reverse engineering the thing itself, but reverse engineering the knowledge, like how they might pack bits or how they might interact with hardware or the file formats, and there seems like there's a lot of value there too.
I think there is, and there's folks from archive.org that have a project to try to document all of the file formats. One nice thing about the retro formats is they tend to be very very approachable, because there wasn't a lot of code space, there wasn't a lot of fast CPUs, so most things tended to be in relatively legible forms. It's much easier to decode a pict or a bitmap than it is if you encounter a JPEG, which is just a bunch of DCT coefficients. There's
right.
So in a lot of ways, it's easier to handle those older formats, and I'm definitely concerned about the sort of digital dark ages where if where we've lost knowledge about how to decode some works. If somebody gave you a I don't know, 123 file on a 5 1/4 inch floppy, how would you be able to recover that?
Right, without being able to go and Google a .123 recovery tool or whatever it is, which would have been my go-to.
Yeah, and 123 might be a bad example because I would not be at all surprised if Excel wouldn't read that just fine.
Yeah.
But maybe if you had a, I don't know, some Amiga IFF image, or something more obscure.
I think that is a, I think that kind of feeds into the open source idea as well, right? It's like as you move away from more open things, open file formats, open tools, whatever, the chance for data loss or data obfuscation forever is like it's very high. And I'm sure that that's a topic near and dear to your heart as a reverse engineer. Kind of, your ability to go and open things back up and reuse them or repurpose them is pretty important.
Yeah, and I'm definitely much more concerned about the closed source files and formats. The wonderful thing about open source is you can probably set up a virtual machine and install an ancient version of Linux and still build that code from 1995 to read something from 25 years ago. But yeah, if you have to find an Atari ST or something, it's probably going to be a lot harder.
I'm just sitting over here thinking you're having a panic attack that 1995 was 25 years ago. It's time keeps on marching.
Yeah, it's back in '95. I read a book by Peter Salas called "A Quarter Century of Unix." That was a history of the 25 years of Unix leading up to that point.
Wow.
And I think we're due for now a quarter century of Linux.
Wow. Yeah.
50 years of Unix and a quarter century of Linux.
That's pretty crazy. Yeah. I mean, the other thing that kind of pops out from thinking about the retro computing stuff is like how close, the lines between like full scale computing. I don't even know how the words here, but like full scale computing versus like embedded computing. Like retro computing seems more like embedded is today, and it is that you need to have that low level control. You need to have compressed code space and stuff like that, and there's a lot of benefit to that, I think. But there's things are moving away from that. Speaking of Linux, I guess systems get more complicated just to be able to do more.
It's really shocking how powerful a microcontroller today is. That the TNC4 that was announced a few months ago, I think it's multi-core, 600 megahertz with a floating point unit and branch prediction and maybe speculative execution. This would have been a incredibly powerful machine a few years ago, and now it's a $10 or $15 throwaway embedded device.
Right. And you have another section on your site about, I'm trying to find it now, but it was about tiny microcontrollers and stuff like that. I wanted to call out the RFID thing you did with was it 2 pins? What was that one?
Yeah. So so this is based on some work that that Scanlime did. She had figured out a way to get a tiny 85 to act like a RFID chip. So I started with her research. I was able to extend it a little bit, make it a little more flexible. At the time, I was carrying 3 different RFID tags and was frustrated when I'd go up to the different doors and had to fumble to find the right card to scan. So I wanted to make one card that I could select the different IDs with. So again, starting with Scanlime's work, I was able to modify her code to compress it enough to fit these multiple IDs into the one. And the actual circuit, like I say, it's just literally a trace on the circuit board that makes a couple loops and connects the 2 clock pins. And it completely abuses everything about this poor microcontroller. There's no power, there's no ground. The clock is being provided by the RF, the 125 kilohertz RF, but it's dependent on the fact that there are protection diodes to rectify that, and it's dependent on the fact that there's enough leakage current through the die to power up the CPU from the clock signal coming in. And it's also dependent on the fact there's enough sort of stray capacitance on the die to keep it running when the signal is being rectified. Everything about this shouldn't work.
Yeah, and it's like I think you wrote, like, it's a testament to the robustness and the process capabilities of chips these days. It's just,
and it worked quite reliably. I mean, the whole passively powered through the RF is pretty magical to begin with, but then just the fact that everything else worked is pretty amazing. With some of them, with one of the ones I've added a few more loops to the antenna, which seemed to make it more effective, and produced enough voltage and current to light up LEDs on the RFID when it gets scanned, which makes it a little more fun.
And so it has to have enough. Does it have to have enough like capacity, straight capacitance to basically power a response as well, or what is the? How much power are we talking about here?
I never actually tried to actually measure the power. I'm not even sure how we could, if we put an ammeter on it, maybe we could see some current going through.
Yeah, the load of the ammeter might take it all down. Big old house of
Exactly.
cards there.
Everything was very fragile in that respect. The So the interesting thing is that with RFIDs, the card itself doesn't transmit, which
Okay.
was really sort of surprising to me. What it does is it shorts the antenna, the two leads on the antenna together, and then the card reader is measuring the power being consumed by the transmitter. So it's
Okay.
basically like half of a transformer. So it measures the current going through its side of the coil, and when the card shorts its side on the antenna, that causes an increased current draw. And so by pulsing that, but by shorting and unshorting the antenna, that signals through the induced current draw what the data stream is.
Oh, that's really. I never looked into that before. That's interesting. I guess that makes sense too, because you're going to have in like a passive system, you're not going to have much power for retransmit. And that's kind of, I guess, there's like farther field versions of this now too, right? Where they're doing the same thing with like radar or something similar, where they're able to, tiny devices are able to basically transmit where they are in a factory or the floor of a warehouse, that kind of thing.
Right. Yeah, I've read about these sort of millimeter wave things, but I'm not. Despite being an amateur extra radio operator, I don't actually know anything about RF. I just kind of muddle through it and hope that I can figure out how to make things work.
Yeah, well, I think millimeter wave's its own, emergent category.
Yeah.
So, well, that's good. What is your RF? We're doing a speed run here through all your projects, but what are some of your radio interests?
So I'm a really big fan of some of the digital modes, like PSK31. That's a ultra low bandwidth, 15 hertz of bandwidth, digital, kind of like a teletype mode. It's really sort of amazing to see how much data you can pack onto a shared channel with PSK31 over single sideband. So there's no carrier. Everything is cosine squared ramped so that it minimizes the sort of splatter. It's a really neat protocol. I also really enjoy the playing with SDRs for a lot of these things. And I think one of the things that SDR that I found just most magical is the realization that the term bandwidth literally means the width of the data, the width of the signal on this RF band.
Yeah, right. Exactly. I had the exact same thing. Like the first time you see a waterfall plot, you're like, oh my God.
You're like, oh, wow. Yeah, the wider it goes, the more data you can send.
Yep. That's right. Yep.
Yeah.
And I don't know. The first thing I had the same reaction to you. The second thing I was incensed that when I was being taught taught radio stuff and communication stuff in school that they did not just show you that right away. Like when you like decode an FM, you're looking at a waterfall plot of an FM station and then you like turn your head sideways and you're like, oh my God, there's an audio waveform. It's just like, why didn't anyone tell me this? It's just it's very frustrating.
It's really neat to see on the waterfall plot how much you can visually pick out that, oh, that's an FM, that's an AM, that's some CW stuff.
Yep.
The spread spectrum frequency hopping things that where you get the blips that sort of race across the waterfall.
Hmm.
It's really a magical way to see this invisible RF world.
Yeah, I'm just amazed that people did it before they had those tools. They're just able to visualize it outside of it. It's just, yeah, there's some wizards among us.
Yes, yes. The, uh, the other part that I really like about SDR is that uh, it brings things back into the software world where I feel more comfortable. That if you ask me to design a super heterodyne regenerative receiver, I'd have no clue. But once I get an IQ waveform, I can probably figure out some way or some libraries to throw at it to get the data out. But trying to do it in an analog circuit is largely beyond what I feel comfortable with. And um, between the SDRs letting me do that in the RF world, and FPGAs letting me do that in the hardware world, suddenly
Hmm. Hmm.
I'm it's made it possible for software people like me and to suddenly have a much wider range of interfaces to the outside.
Yeah, no, that's a good point too. And so, is that like one of the first steps of your project is to kind of get it from the hardware world into the software world?
I think so. I think once we have things in bits, we have a lot of really great tools for pulling them apart, for looking at them, for analyzing them. Um, but yeah, when we're dealing with analog signals on the wire, it's a lot harder. Um,
Yeah, yeah,
although I would definitely not give up my physical oscilloscope. The ability to look
sure.
at a trace and say, I see what's happening is
Right, right.
um,
It's
is-
sanity check, really.
exactly. Um, I recently had with the Spy project, we were having a problem where we were getting some really weird results, and it turns out that if you have multiple drivers on that bus, you don't get a digital waveform anymore. But
Yeah,
the digital inputs are trying to make sense of it, and it's uh, being able to look at it on the oscilloscope and say, this is clearly multiple digital signals being added together and mushed together.
yep, yep.
Saves
Yeah,
us
you
a
see like
huge
half, you see like half signals and stuff like that. You see like blips and yeah,
exactly. So that saves us a huge amount of debugging, or saved me a huge amount of debugging to be able to look at that and realize that it's not a problem in my software. The
yep,
problem is somewhere else.
right. Yeah, it's like a yeah, maybe garbage in, garbage out, but where's that garbage coming from? Need a garbage inspector.
Yeah, yeah.
Well, you mentioned scopes. You also have played around with vector stuff, and vector is part of old oscilloscopes, but also video games and stuff like that. What was your interest with that?
So that definitely overlaps with the with the retro computing side of things. I
Hmm.
really have a affection for the both the aesthetics of the vector games and also the simplicity of a lot of them. That uh, growing up with the Pac-Man and Asteroids era coin-op games, I always felt that I could write that, and I think it's very empowering for as a child to realize that these games were written by very small teams of people, in some cases by individuals.
And in some cases, in hardware.
Yeah, in a lot of cases in hardware. Compared to if you're facing a modern AAA game these days that has $100 million budget and a team of thousands working on it, it's a little that's a little more intimidating to think about trying to build your own version. So yeah, I have this nostalgia for these vector games, for sort of the simpler versions of them, and uh, I've never felt that the LCDs give quite the same feel of the actual the vector displays. Unfortunately, people aren't making CRTs anymore, and a lot of the electronics that were being used to drive the vector CRTs have failed. So I built a project that could generate analog vectors with some dual DACs. And this is definitely a case of throwing more hardware at it. That probably would have been easier if I actually knew how to do any op amp and analog work.
But still, that's great. I mean, like that's the basis of modern computing. I think is just silicon's cheaper. Why not do
Yeah,
it?
yeah,
Yeah.
exactly. Just do it in software. And then I hacked up the MAME emulator to be able to output the start and end points of the vectors. MAME is emulating the original hardware that the cabinets were running on. So it actually gets for most of the vector games, it gets a 10 or a 12-bit XY coordinate to draw to. So I hacked up MAME to print those out to the serial port that feeds into a teensy microcontroller that then drives some DACs to generate those vectors. And the games are really playable, and they're really a lot of fun to see in that on the original sort of displays.
Well, so we've had a past guest, Todd Bailey, another New Yorker, talk about his vector stuff as well. And one of the things he mentioned was like the line hops is like a hard thing. How did you? So did you have to do something in the MAME to redraw the line segments so that they didn't like skew and overlap and stuff like that?
So yeah, Todd's Vec 9 game is absolutely beautiful. I got to play it at Maker Faire a few years ago, and it's a really stunning piece of work. I think he said it's the first vector game written, or first new vector game in a few decades.
Oh, really?
It's
Okay.
really
Well,
a lot of fun. So there are there are a lot of issues that you run into with the fact that CRTs don't move instantaneously. Especially there are two different types of CRTs that I know of. There's the things like oscilloscopes use an electrostatic deflection, and they can move
uh-huh.
at tens or hundreds of megahertz to move the
And
beam
that's just
around.
because you're driving an electric field basically to influence the e beam. Is that kind of the idea?
I believe so. Again,
Okay.
not an electrical engineer. I'm
I think we're just going to
once
say you're
I
close enough, Trammell. Come on.
um, and the other thing is if you open up an old CRT oscilloscope, the tube is like half a meter deep,
hmm
and still only has 10 centimeters of deflection. So it's having to deflect over a much smaller arc.
hmm
But the big vector displays are almost all magnetic deflection, which gives them a much wider angle that they can deflect to. But the uh, the magnetic coils almost have inertia that you can't move them in their state instantaneously. So you have to in your vector generation, you have to essentially model that. So if you want to move the beam quickly from point A to point B, you can set the voltage to the new value, but then you have to wait for the beam to actually get there. So in the firmware for my vector generator, it has some tunable parameters for that sort of thing, so that
Yeah.
you can ensure that your corners stay sharp, and that uh, that the lines start at the right point rather than starting somewhere along the line.
So you're saying the greater deflection is needed just because the screens are bigger? Is that right? Or
Yeah, it's both that they're not as deep, because nobody wants a 3 or 4 meter deep CRT. Yeah, don't
hmm
even know if you could manufacture such a thing.
right,
Um,
right. You need like one of those. What's that glass shape? That's like a glass drop.
yes,
You
yeah,
need
yeah,
like
it's something that just extends out to infinity.
yeah, yep.
Um, yeah, they want larger CRTs. They don't want them to be as deep. So as a result, the magnetic deflection is a much more popular thing to do. And the other thing that I haven't actually looked into, but a lot of the modern, excuse me, a lot of the later vector games had color CRTs, so they could actually do different. They could do RGB colors for the lines. So like the Star Wars vector game is in color, for instance.
Yeah, and you have some. I mean, we're going to be linking all of these projects, of course. Almost everything we've talked about, I think, here today has a page for it, so people can definitely go and check out all this stuff. But yeah, the color, the Tie Fighter game is especially nostalgic for me. That's awesome.
And there was a fun. I had a fun write up on this in Travis Goodspeed's journal a year or two ago, and I think through the magic of their polyglot file formats, that if you load it as an animated image, you get the replica of the Tie Fighters
Oh, that's
racing
cool.
across the screen.
That's really cool. Well, let's see. So we've talked about a lot of the stuff on here, but not everything, of course. Um, you've also reverse engineered robots. I thought that was kind of interesting. What was the deal? And a lot of this stuff I should mention too is coming through NYC Resistor as well, which you were a prominent member.
So when I lived in New York, we were I was at Resistor 3 or 4 nights a week, and most weekends. It was really sort of like the living room. For a lot of us in New York, none of us had huge apartments, so having a shared space for tools and projects was absolutely a necessity. And Resistor was a wonderful, welcoming place, a very diverse and inclusive set of members. And what I really love about Resistor is the mix of artists and engineers and fashion and music and textiles and paper crafts, and the view of technology uh, was just went across pretty much everything. That it wasn't just people doing computer security or just people doing 3D printing. It was a little bit of everything. Um, so yeah, so somehow ended up with a set of Puma robot arms that had been removed from their factory with a set of bolt cutters. So the no wiring harnesses, no motor controllers, you know just some
Just
short
stubs. Yeah.
some short pigtails. And as a fun project, I uh, with spent some hours with a multimeter just doing continuity to figure out what was wired to what, and built an open source library to do the inverse kinematics for the 6 degree of freedom arms. Also, just to try to understand a little bit better how to interface with them.
Yeah.
They, they're relatively high precision, and relatively powerful. So we had a fun project at my office where we built a shuffleboard attachment for them, and then invited some of our colleagues to build their own AIs to play tabletop shuffleboard with the robots.
And I'm sure they're no better than the drunk bar denizens that are normally playing shuffleboard.
Yeah, they were slightly better, but the repeatability was really hard in shuffleboard. That
Yeah.
I think a lot of it comes to reading the sawdust on the table, and
Yeah.
they didn't have a view of that. They only had a view of uh, the um, uh, the puck configuration. So with that limitation, they still did pretty well. But a good human was able to beat them, unfortunately.
That's good. No. It's okay. We're okay with. I think we have a limited time span for humans beating robots at anything. Let's just revel in it for now.
Yes, when AlphaGo switches over to shuffleboard and ping pong, then we'll
Yeah. Oh yeah.
yeah.
It's all over. So you had mentioned you'd written about the reverse engineering process of that. I was interested how you said you used a scope on the lines to actually sense the quadrature decoding. Could you explain that a little bit?
Unfortunately, they didn't come with any data sheets, so what we had were just a bunch of wires coming out. So with the multimeter, we were able to find the continuity, and we identified the DC motors pretty easily, and then we also identified for the quadrature encoders which which four wires they were, and we knew that they would have a power, ground, and then sort of an A and a B output. Um, so we made a good guess as to which was which. Luckily, did not blow up any with reverse polarity, um, and were able to identify that they were, uh, that we had to put. That first, it looked like there was no signal coming out of the A and B output lines, and we realized that we needed to put external pull-ups, and that they were being pulled down by the encoder. And
Mm.
a lot of this came from sort of having seen a quadrature encoder before, having some ideas about what is it likely to be doing. Um, and a lot of this reverse engineering just comes down to that sort of, making guesses about, how could this work? What are the likely ways that it could
Mm.
work? And, and then trying things, with four wires, there are what, uh, 16 ways that it could be wired up. And
That's right. Yeah.
hopefully only
Right.
one of them causes things to blow up, and hopefully we don't pick that one.
That's good. That's good. I mean, I guess the thing I was wondering about too is like, so I haven't done much with motors. Just even thinking that there was like an encoder on board and like understanding that, and looking at it on a scope is interesting. Just kind of and like the encoder itself, like I don't know if it was Hall effect or if it was like a optical or how it was actually being encoded, but just thinking that like there would be one on there. I just don't work with robots, so I don't know. But like that seems like a smart thing to understand there, and thinking about then pumping that into a system.
And the thought was these things need high repeatability, and trying to run open loop with a DC motor is just not going to be very accurate. It's not going to give it that repeatability. So we figured there's probably going to be some sort of encoder. And when we disassembled part of the motor housing, we saw that the motors had shafts coming out both the front and the rear, where the front went into a gearbox that then drove the arm mechanism, and then out the rear went into a kind of light duty plastic box of some sort. So that was a pretty good hint that there's something in there that's probably doing some sort of counting or encoding. Um, and the one of the issues we ran into is a lot of the servo controllers, the DC motor controllers, weren't well set up to handle the quadrature input. So, like a lot of things, ended up building a small microcontroller based system that would do some translation layers uh, on those pulses into counts that we could then feed um, into a closed loop servo controller.
Put it back into software and the realm that will make it
Exactly.
hackable. So
That
that's
move it
good.
to somewhere we can do our own PID and tune it ourselves.
Well, this all kind of rolls up together to the fact that the thing we haven't really, I guess we kind of mentioned it, but you do security research. That's like your gig, right?
That's
I mean,
my day job.
yeah.
When I'm not taking other things apart, I take things apart for to try to figure out where are the security vulnerabilities and what do we need to work with. Where can we work with the vendors to try to uh, improve the laptops and the servers that we depend on.
Right. And you've done you published about some of it on your site about the YubiKey and things like that. But I mean, what is your uh, I'm always kind of sensitive. I don't know how much security people are allowed to talk about, but what are you allowed to talk about in the security world and the things that you work on?
I've been really lucky that most of the work that I've done in the security space has been has ended up in the open. So I've been able to present at CCC and DEF CON and events like that about this work. Um, the one uh, that sort of got me into that field was a few years ago. I found a firmware vulnerability in MacBooks that allowed someone with access to the Thunderbolt port to flash their own firmware into the MacBook mainboard.
Which is kind of a big deal.
Kind of a big deal.
Yeah.
This was because it was trendy at the time. We gave it a fun name. We called it Thunderstrike since it came in through the Thunderbolt port, and this it got a lot of press, and in a lot of ways I think brought firmware vulnerabilities into much much more well known um, in the community. The big problem is that a lot of folks have always assumed, oh, if an adversary has hands on the hardware, it's game over. And I think that's a much too limited sort of view. I think that it's possible to have threat models that allow adversaries to have either temporary hands-on or perhaps even more extended time with it, and we can still possibly have some faith that the systems will be okay. And part of that is sort of demonstrating here are places where we have problems that we need to fix. Um, and Apple took the Thunderstrike vulnerability very seriously. They released patches for 8 years worth of hardware, which is just absolutely amazing.
Right.
Um,
Right.
you know,
That's no small task. That's a lot of regression and testing and making sure it doesn't bork
yeah,
everyone's
yeah,
hardware.
exactly. So after that one, I've also shifted into more trying to think about how do we build more secure systems. So I've been working with the core boot community on open firmware for these machines, and then also helped start a project called Linux Boot, where we're trying to replace the proprietary firmware in servers and some laptops with Linux, which it is a large amount of code, but it's a fairly well tested and fairly uh, widely understood code base. So rather than having a few tens of people at some small firms doing firmware development, this lets us take advantage of the fact that everyone is looking for security vulnerabilities in Linux, and typically when they're found, they're patched relatively quickly. Um, the other big thing that we like about open source firmware is it means it's possible for people to build their own versions, either for research or for customization, but also to patch the vulnerabilities on their own schedule. A lot of this hardware never ever sees any firmware updates because once a system's sold, most of the OEMs are done with it. But if you can build your own firmware, you can patch firmware vulnerabilities, and the community can also then take over abandoned hardware and continue to support it. So if a system is important enough to you, you can either do it yourself or you can find people who might be able to help you out with it.
Yeah. So could you give so you said like tens or dozens of multiple dozens of people that are doing it. When you speak about that, you mean like internally they would be writing custom firmware for boot imaging and stuff like that?
There's only a handful of companies called independent BIOS vendors that make most of what people think of as as the BIOS, the UEFI for their
Oh,
computers. Um,
okay.
and the bulk of the code is actually coming from Intel's EDK2 reference implementation for UEFI. That the in one of my talks, I have a chart showing the bulk of the code comes from that. The device manufacturers will pay the independent BIOS vendors to port that reference implementation to their new servers or laptops, and then the OEMs will do some amount of customization on top of that when they buy it from the ODMs. Um, so this means that any changes need, uh, if there's a security fix, it might have to go through 4 different companies before it actually reaches the end user.
Yeah, that's a little that's unlikely to be as secure or as helpful. So what would be the alternative is this Linux thing that's on there instead then, and then how does that look different for a OEM? They would basically just be able to build it and load it on there, or is this meant as an end device or sorry an end replacement for the end user that they could then load onto something they've already got as well?
Well, the vision of the Linux Boot project is that the OEMs uh, will do the port themselves, and that they'll sell machines with this with either Core Boot or Linux Boot firmware built into it. where the end customer who now owns the computer has the freedom to modify it if they want to. In a lot of ways, I think this is very similar to the Unix wars of the 1980s and 90s, where all of the major manufacturers uh, frequently made their own CPUs. They also then made their own versions of Unix, and they were all incompatible in vague ways with their own sets of security vulnerabilities. Yes, you had the HPUX on the PA RISC hardware. You had Solaris on the Spark hardware. You had AIX on the Power hardware. And then pretty much out of nowhere, Linux came about and took over. And very quickly, the operating system became no longer a distinguishing feature for the OEMs. That they were now competing on making better commodity hardware that ran Linux well. And I hope that a similar sort of dynamic will play out in the firmware space. That the all of these customized, value added UEFI implementations will end up becoming legacy, and the OEMs can focus on using the common Linux boot or core boot firmware, and focus on just making better systems that run that well.
Do they see it their value add as something that is like competitive advantage? Like, are they resistant to this sort of thing?
There's a lot of sort of not invented here going on with it. Yes,
Okay.
that they
Yeah.
do think that they're providing some value. Um, from the view of large enterprise customers, it sometimes is negative value because it's essentially a vendor lock-in. That if you end up having to build your procedures and your systems, um, customized to some vendor's specific firmware implementation, it makes it much harder to migrate to other vendors.
And yeah, I can imagine the vendors like that then too, because they want lock in and end users don't. So yeah, this is that's fascinating. How long is the Linux boot project been going on?
I guess we're Linux Boot's in about going into its second year. I gave a talk about it at I think 34C3. Losing track.
Yeah, that's right. Give enough talks and they all start to blur together.
Yeah, and this is has some backing from the folks at Google and Facebook who deploy hundreds of thousands of machines. So they're very interested in being able
Right.
to control the firmware on those machines.
Yeah, I could. Yeah, with very large security implications if things go wrong. So I can imagine they would be interested in that. And there's a bunch of bright people there too. So how close? I guess are you? Where are you in the life cycle of handing off the repo keys? Have you already done this or?
Well, since we have these large contributors from the hyperscalers, I luckily don't have to do very much anymore. That there are people doing code reviews, there
Okay.
are people doing documentation, there are people writing deployment guides, and I just get to hang out in the Slack channel and talk with really bright people about firmware things.
So what's next then? What's the next? So you'd mentioned one new project. I've already forgot what it is. We've had enough top project talks here, but what are you working on these days that you're excited about?
So I'm right now working on extending SpySpy to handle some more different flash devices. Starting on the security front, I'm looking more at enclaves, specifically the AMD SEV and Intel SGX. From the security perspective of what are the risks of moving confidential computing into these things. Um, uh, I'm excited about the some of the community support for Linux boot on some Supermicro servers, along with micro BMC, which means that these machines will now boot almost entirely with free software from the BMC to the x86.
That's
I'm
cool.
trying to think what else is going on, and then the thing that I'm currently working on, hoping to put together a guide, is how to build your own custom firmware for these IKEA lamps, that might be my next maybe my next talk at Congress or somewhere else.
I think that's what you had mentioned earlier too, so that's good. And you are in Amsterdam now, so you no longer are in New York. You've hopped the
Yeah.
pond.
So as of April, I'm now full time in Amsterdam and really enjoying it. We tell folks it's the new York. It's
That's great because New York is New Amsterdam. Is that the idea?
exactly.
Yeah. So new Amsterdam. It folds back eventually.
Yeah, and
So
there's a really wonderful tech and art scene here.
yeah,
This Friday, there's a fun live coding, music, and visuals event that we're going to, um, and uh, it's really a wonderful place to be.
I mean, I'm just jealous when you post pictures about working on the train and biking and stuff like that. So more lifestyle jealousy for me than, but the scene is good too. That's great.
Yeah, well, the train. I'm uh, trying to reduce my carbon footprint a bit. I've flown uh, far too many hundreds of thousands of miles in my life, so I'm trying to go just via the train. Had 3 conferences in 3 different countries in 2 weeks, and did that all via the train, night train, and ferries, and that worked out really well.
Yeah, that's awesome. Yeah, the flying thing that's on my list too. Where can people find you online? How do they get in contact with you?
So you can see the projects like you mentioned on trmm.net. I'm somewhat active on Twitter, QRS, also on Mastodon, QRS at mastodon.social. Um, and yeah, the website has more ways to get in touch with me.
Awesome. Well, Trammell, thank you so much for talking about all your projects here. I'm looking forward to seeing you at future conferences and seeing all the other things that you put on your website. It's great to see the things that you've done.
Chris, it's been wonderful chatting with you, and really had a lot of fun talking about all these projects. It's been a fun. I love documenting them, and I'm glad. I'm really glad that you enjoyed reading about them.
All right. Well, thanks, and we'll talk to you soon.
Okay, take care.
Once again, we'd like to thank our sponsor for this episode, Roden Schwartz, a leading manufacturer of value instruments designed to help you maximize your bench's performance for everyday applications. They just announced an industry first, complete solutions with all the upgrades up front for one price. Now through December 31st, 2019, save up to $10,000 on Roden Schwartz solution packages that come with fully loaded test and measurement instruments right from the start. When you invest in Roden Schwartz products, you get the highest quality engineering, plus all the bandwidth, channels, inputs, memory interfaces, and signal generation you'll ever need. Learn more about Roden Schwartz value instruments and this limited time promotion at askanengineer.us. That's askanengineer.us.